So I think this is the last example. Let me show you the last example. It's a nice example. You have again current going through the cable, and you have a rectangular loop which has a distance h for this side and distance h plus w for the lower side, and the side has length L, okay, and the width has W. So the question is, if your current is changing over time with this equation, A plus B times T, and A and B are constants, okay, and T is time. So your current is changing, and in the first place, find the magnetic flux through the loop. So we know what a magnetic flux around a cable which has a current I flowing through it, don't we? Mu0 times I divided by mu0 times I divided by 2 times pi times the perpendicular distance r, right? If you have a current flowing in any direction, whatever the direction is, keep a distance r, perpendicular distance r at a point, the magnetic field at this point is nothing but mu0 times I divided by 2 pi times this distance, okay? So we know what the magnetic field at any point from the cable. If I know what the magnetic field is, and if I know the area, then I can calculate the flux. But the thing is, through this area, the magnetic field is not constant, right? Only in the lateral direction, at any points on this lateral direction, the magnetic field is constant because they have the same distance to the cable. But if you go in this direction, the magnetic field is changing. So how can you calculate the flux with the changing magnetic field?
First we find the magnitude and their direction.
Okay. Well, the direction on all over the region is the same magnetic field direction, right? So it's, if the current is toward right, if the current is toward right, the magnetic field in this region is into the page, right? By using your right-hand rule. So how do I calculate then? Do I know what the expression of the infinitesimal flux? What I mean by infinitesimal flux is, let me show you this. Where is it? I don't know, board marker. Okay, I think I have already done on this here. If you have a changing magnetic field, okay, the flux is not just the strength of the magnetic field times the area, but instead of this, the flux is an integral. So this is the expression for the infinitesimal flux, and this is B dot dA. dA is the infinitesimal area element of this rectangle. So I will divide. This means that I have to divide this rectangular region into small rectangular pieces, okay? And each of these small pieces has an area of dA, okay? And I will do this in such a way that in each small pieces, the magnetic field is the same all over the small piece. So, is this small piece a rectangular region in this direction or this direction? I want that this small area dA has the magnetic field the same all over the small area. So it must be a stripe which is parallel to the wire, right? If I can divide this rectangular loop into small rectangular stripes. Şeritlere ayırıyorum. Küçük küçük şeritlere ayırıyorum. Bu şeritler akım kablosuna paralel şeritler. Akım kablosuna dik şeritler değil, akım kablosuna paralel küçük küçük şeritlere ayırmam zorundayım. Niye? Çünkü her şerit üzerinde her şeridin akım kablosuna uzaklığı her noktanın aynı olduğu için her şerit üzerinde manyetik alan aynı. I do this, okay? I show only one rectangular stripe as representative of the infinitesimal flux. So this stripe is very thin, which has the thickness dr, and I know what dr is. Dr is infinitesimally small piece of length. So in the vertical direction, it has the dimension dr. In the lateral direction, it has the dimension L, right? This stripe has this side L, and on the vertical direction, it has the width as dr. Because I measure the distance from the wire of the stripe as r. If this distance is r, and in the same direction, in this direction, the infinitesimal length is dr. If this were x, this infinitesimal length will be dx. If this was y, the infinitesimal length on this y direction is dy. So this is the same procedure for all kinds of such things, right? I have done many times to calculate the electric field, electric charge of a surface distribution, electric charge of a line distribution, light, which is multiplied dl by the lambda line charge density, and multiply dA by sigma, which is the surface charge density, remember? So I do the same. I just divide this region into small pieces so that on each small piece, on all the small piece, the magnetic field is the same. So what is the magnetic field on this stripe? Because dr is such a small length, on this stripe everywhere, although this is a rectangle, the magnetic field is the same. And the magnetic field is nothing but mu0 times I divided by 2 pi times this distance r. And once I know what the magnetic field all over the stripe, I can calculate the flux all over this stripe, right? And the flux all over the stripe is nothing but the magnetic field strength, B, times the area of this stripe. And the area of the stripe is L times dr. I'm talking about the stripe. I'm not talking about the whole rectangle. Okay? So, B is mu0 I divided by 2 pi r, and dA is L times dr. Because I'm talking about the area of the stripe, not whole area of the rectangle. Because I divide whole rectangle into small stripes. So this is the expression, B times dA is the expression inside the integral. Okay? And I'll put this expression inside the integral to find the integrand, mu0 times I divided by 2 pi r times L times dr. So once you get an expression d of something inside the integral, that means d of something is the variable of this integration. And the variable of this integration is r. And r is changing for this loop from h to h plus w. So this defines the limits of the integration. And the limits of the integration is from h, when r is equal to h, it starts over this rectangle and go through the rectangle to h plus w. So this is the limits of the integration. And I got the expression which depends only on r, dr divided by r. All our other terms are constants. You can take outside the integration. Mu 0 times I, L, 2 pi. Although I is changing over time, I can take I outside the integration because it depends on time, not r. Okay? So taking the integration of dr over r is easy, just ln r. And if you put the limits, you get the result of this integration as this constant mu 0 I L divided by 2 pi, the natural logarithm h plus w divided by h. So this is the flux through all this rectangular region which sides L and W. But this flux is not constant over time because I is changing over time, right? So I can take the time derivative of the flux to find the electromotive force through this loop. And the electromotive force, if you imagine this loop as a rectangular wire, then the electromotive force over this wire is minus d phi b divided by dt. And all this expression, only you take the time derivative of I, the current, because I is changing. If this I were constant, then there will be no induced current on this rectangular area because d phi over dt will be 0, because I is constant. But now I is changing over time, so I have a constant electromotive force because I depends linearly on time. And di over dt is nothing but just b. So you replace this di over dt by the constant quantity b. And you get the electromotive force. With these given parameters, b as 10, h as 1 centimeters, and w as 10 centimeters, and the length L as 1 meter, you can calculate what the electromotive force is. Just by plugging and chugging the numbers, you get the electromotive force as negative 4.8 microvolts. So if you have a resistance of this loop, wire loop, and you will have a current through this loop which has an effective battery strength as 4.8 microvolts. What is the induced current I prime over this loop? If this current has a resistance R, you can easily find this induced current by just dividing epsilon by R, right? And what about the direction? Since this B is a positive quantity, the flux will be increasing, right? Because I is increasing. With B is a positive quantity, whatever A is, A might be a negative quantity or positive quantity, it doesn't make any difference. If B is positive quantity, I is increasing. If I is increasing, the flux is increasing through this rectangle. If the flux is increasing, then the induced current will produce a magnetic field in such a way that this magnetic field opposes the increase of the flux. So it must be in this direction, because the current I is producing a magnetic field which is into the page, and the induced current must produce a current, a magnetic field which is out of the page, because the flux is increasing and the magnetic field induced by this current is into the page. If the flux is increasing, then this induced current must produce a magnetic field which is out of the page, right? And this is only possible when the current is flowing in the counterclockwise direction. So this is the last example, I think, and I finish the chapter.